This is the 7th lecture in the first semester Java course presented by Savage River Research. To view all of the currently available lectures, point your browser to savageriverresearch.com and click on Open Courses. This lecture assumes that you've completed all the previous lectures and are prepared to proceed with Lecture 7. But before we begin, let's review the solution to the programming problem assigned at the end of Lecture 6. This was the problem description for Program 6, which simply requires you to declare 5 text strings, and actually they could be composed of any combination of the alphabetic characters on your keyboard. But given the 5 strings shown, the output will capitalize and concatenate those 5 strings, just as shown here, then report the total length of the concatenated string, then report the 5th, 13th, and 23rd uppercase letters of the concatenated string. But your solution has to work with any set of 5 strings that have at least 23 letters in total. You have to have 23 letters in the concatenated string because the third output requires that you output the 23rd letter of the concatenated string. And here I've simply reversed the alphabet. So if your code will work with the example I gave in Lecture 6, it'll work with any similar set of strings. So here's the given declaration for the 5 strings. To concatenate them, I'll declare a string variable concatenate. Wherever possible, it's best to use meaningful variable names. The actual concatenation is accomplished by using the plus operator in this context. It is the compiler's job to recognize that any plus operator with a string to both sides requires that the strings be joined in the order they're shown. And we looked at that in the last lecture. The conversion to uppercase is accomplished by using the toUpperCase method. Class string, like most classes, has an extensive set of methods to manipulate the data contained in a given object of that class. And in the last lecture, we looked at the documentation for each of these methods. So for each of those strings, a call to the toUpperCase method converts every individual character in the string to its uppercase version. Having concatenated the 5 strings, I can determine the length of this composite string with a call to method length. And once again, method length is found in the documentation for class string. So now I have the string variable concatenated, calling method length, a method available to any object of class string. Concatenated is the name, the identifier, of an object of class string. And as noted in the documentation, that method returns the length of the string as an integer value. And in the code, that value will be assigned to the integer variable concat_length, which was declared on line 14. And now, if you want to get the third required output, you're going to have to determine the 5th, 13th, and 23rd uppercase letters of the concatenated string. And that too is covered in the documentation. Method charat will retrieve the character at any index, any place in the string that I specify. But charat, like many of the methods in the JDK, requires that you read the description of the method. So if you click on charat, the documentation will bring up this description. You have to read the description of char_at closely. Maybe I should blow that up. Because method char_at was written to specify that the first character in any string is at index 0, which means that if I want the 5th character in the concatenated string, I have to specify the index as 4. And if I want the 13th character, I have to specify the index as 12. Then if I want the 23rd character, I have to specify the index as 22. So now I have the characters at what you and I might describe as the 5th, 13th, and 23rd positions, and I'm assigning those characters to the char variables 5th, 13th, and 23rd. Now all that remains is to write the output. Here's the text string specified by the client. And here's the line of code that will produce that output with the string variable concatenated attached to the end of the literal text string. But once again, it is the compiler's responsibility to note that concatenated is a string variable. So it writes the actual string contained in the string object identified by the reference variable concatenated. The next line of required output, this line, is generated by this line of code, which appends the int variable concat_length, which was declared and initialized on line 14 to the literal string 2.space, capital T, small h, etc. And again, it is the compiler's responsibility to enforce the Java rule for method println, which requires that if the parameter contains a string literal concatenated to an integer variable, then it is the character sequence representing that integer value that is printed out. In this case, the character sequence 2, followed by 6. And finally, the last text string specified by the client. Take a moment. Make sure you understand just how the println method arrives at this output. Just to make sure, let me take this one step at a time. The println method will read its parameter from left to right. The first part is simple. After reading the opening quote, println just displays everything it reads until it encounters this, the \n. Even though the \n is within a set of quotes, it will not be printed. The println and the print methods interpret the \n sequence as a new line instruction that will drive the cursor to the next line. Let me mark that current cursor position with this star. Now, moving again to the right, it encounters this plus symbol, which it interprets as a concatenation operator, since it has a string to its left. So when the println method encounters the concatenation operator, it will print the string literal to its right, starting from the current position of the cursor. As the println method continues to evaluate this parameter, moving from the left to the right, it will recognize that this concatenation operator has a string on its left and the name of the char variable 5th on its right. Remember that the char variable 5th was declared and initialized here on line 15, and it will print the actual value of the char variable fifth right here. Moving again right, it encounters another concatenation operator and prints the literal string, the character, comma, followed by a space. And the same sequence plays out to print the 13th letter of the concatenated string, capital M, which is actually at index 12 in the concatenated string, since the first character in any string is indexed to 0. And finally, W, the 23rd character in the concatenated string, which of course is found at index 22. This is what we've covered so far in lectures 1 through 6. And here's where we're going in lecture 7. We'll look briefly at comments, then go to work on the scanner class. Comments are simply notes that you write yourself, or to whoever has to modify your code after you move on to your next assignment. The simplest comment is the single line comment. Anything after the two adjacent slashes on the line will be ignored by the compiler. On that single line, I can write anything I choose, including reserved words, mathematical operators, and what might even appear to be executable code. It'll all show up as green, and it will be ignored by the compiler. This is the format for a block comment. Everything beginning with the slash asterisk, and ending with a asterisk slash will be ignored by the compiler. This comment type cannot be nested. This is a JavaDoc comment, a slash followed by two asterisks. This is a special version of the previous block comment that allows comments to be documented by the JavaDoc utility program. Everything beginning with the slash asterisk and ending with asterisk slash will be ignored by the compiler. This comment type also cannot be nested. Okay, now let's take a look at the scanner class. This is slide 74 from lecture 6, in which I first referenced the scanner class, but in that lecture I was using it primarily as a way to introduce the use of the reserved word new, which is required to create an object of any class other than the string class. You do not have to use new to create an object of the string class. The scanner class allows us to bring keyboard input into the program. But like most things in Java or any programming language, it requires some explanation. And the first thing that needs to be explained is the first line, which starts with the reserved word import. Like all reserved words, keywords, import may only be used in the manner prescribed by Java. And in fact, this is the only way you will see it used. Its purpose is to instruct the JRE, the Java Runtime Environment, to search the JDK, the Java Development Kit, to find the source code file for class scanner. Once the JRE has imported java.util.scanner, this line instructs the JRE to create a new object of class scanner using that imported code. The class name is scanner with a capital S. All of the class names in the JDK begin with a capital letter. It is employed here to identify the variable name keyboard as a reference variable pointing to an object of class scanner. The keyword new instructs the JRE to create a new object of class scanner and assign the address of that object to the scanner reference variable keyboard. Once this line is executed, keyboard will be a reference variable that contains the address of the place in memory where an object of class scanner has been created. This is the sequence that tells the JRE to create a new object of class scanner, but class scanner requires a parameter, this parameter. Most of the JDK classes that you and I will use require a parameter, and most of the classes we'll create to tackle the complex problem domains we'll encounter later in the semester will also require at least one, sometimes several parameters. This parameter is actually another object, one which is linked to the keyboard by the JRE. That object is system with a capital S, system.in. The system class is part of the Java API, the Java Application Program Interface. Several objects of that class are created when you start Eclipse. The objects we're interested in here, system.in and system.out, and again, these are created when Eclipse or any other standard Java IDE starts up. You and I do not have to create a system object. It has already been created for us. We simply have to state that we're going to use it. But class scanner and almost all other classes are different. We have to create scanner objects if we want to use the methods that the scanner class provides. And to create a scanner object, you have to pass it a parameter that tells the scanner the object it's supposed to scan. In this case, system.in, which is your keypad. You're telling the scanner object to scan the keypad. But first we need to get user input. And we'll do that here on this line using system.out, where out is also an object of the system class, an object created by the API, and that object is used to access the print method and the println method. These methods will print whatever they receive as parameters to the console. System.out, like system.in, is an object of class system. Both of those were created when you started Eclipse. But system.out features a number of methods dealing with output, including print and println, which send their parameters to the console. All objects of the system class are available to us because they were created by the Java API, the Java Application Program Interface, which started when you started Eclipse. But to get access to the scanner class, we had to tell the JRE where to find it. Now, if I comment out the import statement for the scanner class by placing 2 slashes in front of it, I'll get a compile time error. Note that Eclipse also underlines both places where scanner is written with squiggly red lines. That's Eclipse's underlining, not mine. This is Eclipse telling me that the compile time problem lies right here where the red lines are. And if I put my cursor on the error flag, Eclipse will tell me the cause of the compile time error. The word scanner cannot be resolved to a type. Without the import statement that directs the JRE to import class scanner into the code, scanner doesn't exist. So the obvious question is, why doesn't the JRE the Java runtime environment? Why doesn't the JRE simply import everything in the JDK, the Java Development Kit, every time it starts up? Why not? Then everything would always be available. You don't need import statements. Well, consider this. In Lecture 2, we looked at the bin folder for the compiled code for the simple shell, and this is what we saw. This is how much compiled code it takes to create this simple program, program 1.1, that does nothing. And if we added a few simple lines, it got a little bigger. But when we imported the scanner class, it got considerably bigger. If we tried to import everything in the JDK, the code would grow exponentially just to make everything available, most of which we had no use for. In fact, the compiled code would be unmanageable. That's why we use import statements for everything other than the absolute essentials. It's an excellent engineering philosophy. Don't bring anything in unless you're going to use it. So now we're back here. I put the import statement back in, but I still have this peculiar little light bulb symbol that's been with me all along. And if I put my cursor on it, Eclipse will tell me resource leak. Keyboard is never closed. Now, remember, keyboard is a reference variable pointing to an object of class scanner. That object takes up space in memory. Now, that's immaterial in this small program. I can leave that light bulb in there, and there's no harm done. But suppose it's a commercial-grade program creating instances, objects of some class, in a loop, executing every time a new user logs in. Sooner or later, you're going to run out of memory and crash. It's a classic problem in C and C++. But in Java, you'll get this warning. It's not a compile time error. The code will still run with this light bulb. But all you have to do is close the potential memory leak with this line of code. The scanner class has a number of methods, including a close method that releases the memory occupied by the object. And any scanner object can be closed simply by executing the close method as we're doing here. And note that the light bulb is gone. Okay, let's run the code, line by line, see how it works. On the first line, we declare an integer variable, first underscore int, initializing it to 0. On the second, we declare keyboard to be a reference variable pointing to an object of class scanner. Then create the scanner object with the reserved word new, passing the system.in object created by the Java API. The next line executes the print method. The print method is one of several methods all available to any system.out object, and that method will write the text passed to it here in the parameter to the console output. Now, execution moves to the next line, line 11, where absolutely nothing will happen until the user types something on the keyboard. Whatever sequence of integers the user types will appear. Suppose the user types 67. Then 67 will appear here. If I made a mistake, I can correct it, backspace over the 7, add a few more integers. But now nothing more will happen until the user hits enter. When the user hits enter, two things happen in sequence. First, the integer value 67, or whatever I just typed in there, is read from a buffer maintained by the system.in object, which tracks all the typing, including deletions and corrections. As soon as the user hits enter, the contents of the buffer is assigned to the variable first int. Then execution moves to the next line and prints the parameter in the println method. Now, as we discussed previously, the part of the parameter enclosed in double quotes, this part, is printed out exactly as shown in the parameter. First integer space equals sign space. A literal is followed by a plus sign, which in this context appends the sequence of characters representing the integer value currently stored in the int variable first int, the value the user just entered on the keyboard. Then execution moves to the next line and returns the memory occupied by the object referenced by the keyboard reference variable. That memory would now be available, used anywhere for any remaining computations. Now, at this point, it would be worthwhile to take a closer look at the scanner class as it's outlined in Oracle's Java documentation. This is slide 148 from lecture 5, and if you followed that lecture, it should be fairly easy to call this website in your browser and navigate to this page, which appeared on slide 76 of that lecture. Now, if I enter the term scanner here in the search box, I'll get a drop-down menu, but I don't need to select from that. I'll just hit enter, and I'll be taken directly to the documentation for the scanner class, which gives a general introduction and some examples like this one, which is structurally the same as our use of the scanner method nextInt in example 7.1. Here they are side by side. The documentation contains thousands of examples like this, but some of them are beyond our current Java expertise. We haven't covered loops yet or delimiters. So for the moment, let's just deal with the scanner methods you should be able to use at this point in your studies. Put your cursor on the slider, depress the left mouse button, and slide down the page. And note that there are actually two nextInt methods in class scanner. One with no parameter and one with an integer parameter. The principal difference is that this version allows me to specify the radix. We can write an input program to read user input in a binary, octal, or decimal base. And that will become important later on when we dive into cryptographic analysis and networking. But right now, we're going to stay with the default, the decimal numbering system. So, to see how the class scanner method nextInt behaves, click on nextInt, which should take you here. Now, as we've already seen, the purpose of nextInt is to read the input the user entered from the keyboard and return a variable of type int. But what happens if the user enters something other than one of the 10 digits, 0 through 9? Suppose the user enters 67%, or any character that is not one of the 10 digits, 0 through 9. What happens then? Well, I don't know either, so let's try it. Apparently Java is not happy with us. But this is not a compile time error. Eclipse catches those before the code can be run. You have to correct any compile time error before the code can execute. This is another runtime error. As long as the user enters valid information, the code will run. If the user enters invalid information, a program will crash. But how do you know what's valid? Well, right here under throws, the program will throw an input mismatch exception if the next token does not match the integer regular expression or is out of range. The integer regular expression defines a set containing the digits 0 through 9 plus the plus and minus signs. Anything else, including a space, will throw the exception and identify the line of code that generated that exception. Now, obviously, you don't want to write programs that simply crash whenever the user enters invalid data. And in later lectures, we'll revisit this topic to see how you can write code that will handle this problem. But in program 7.1, the code simply informs the user that an incorrect data was entered and terminates. That's called a crash. And crashes are not popular with users. So you need to write code that doesn't crash. What we really want to do is define the correct data, the correct set that can be entered, and give the user another opportunity to enter it. And we'll explore those techniques later on. But right now, let's try to expand our competence with the system.in and system.out objects. This is slide 115 from lecture 5, which assigned this program, program 5. The detailed solution to this program is given on slides 5 through 42 in lecture 6. And a variation on the structure of that solution, which reduces the lines of code required to solve the problem, was offered on slide 40 of lecture 6. So let's see if we can put some of this to use in program 7. In 7, all our client wants us to do is modify the code we wrote in program 5 to have the user enter the values for the 3 radii. And the requirement is that the program runs exactly like this. On startup, program 7 will display the line, enter the largest radius. And here I'll use the same numbers that we hard-coded, using double literals, the same ones we used in 5. So the first value in is the largest, 9.6435. Now, nothing will happen until the user hits enter. When that happens, the program must display enter a small radius. And again, the program simply sits waiting for input. So now I enter 2.6. And again, nothing will happen until the user hits enter. When the user hits enter, the program displays enter another small radius. And again, the program simply waits for input. Now I enter 3.715. And again, nothing will happen until the user hits enter. When the user hits enter, the program displays the calculated Ariadne and Forbath numbers, whatever those are, and terminates. Now, this was the code for program 5. All you have to do is adapt it to meet the changing user requirements, which is a lot of the work in software engineering. I mean, clients always want changes. Now, my suggestion is that you pause the lecture and try to code the required changes. Find out whether or not you actually understood the topics we just discussed. Once you've coded your solution, start the lecture again, and I'll present my take on the solution. Okay, if you're ready, here's all we had to do to satisfy the client's change order. Add an import statement that allows access to the scanner class. These are the 3 doubles that we coded with the literal values originally specified. But now the user will be entering the actual values used to calculate the Ariadne and Forbath numbers. And I generally initialize all declared numeric values, integers and floating points, to 0, but that's just a habit left over from my days of writing C code in cryptography domains. In this case, it's immaterial. Now, declare 3 more doubles to hold the calculated areas, and 2 more for the Ariadne and Forbath values. Now, all I have to do is to create the scanner object and execute the appropriate output statement, then employ the next double method supplied by the scanner object to assign the user's input to the appropriate double variable for the largest radius. Of course, the obvious question might be, where did I find this method, next double? Where'd that come from? And the answer is the same documentation where I found next int. And if I click on next double, the documentation will take me to a detailed description of next double, which indicates that the behavior of next double is similar to next int, other than the fact that the regular expression for a float includes the decimal point. Then get the remaining 2 radii for the smaller circles using similar code. Now, let me close up all these spaces and restrict my view to the main routine so I can fit all the code in. And once I do that, we can see that the calculations and output statements are simply adapted from Program 5. Now, remember in Lecture 5, I reviewed the use of the math class and the named constant pi on slide 98. Now, once again, notice that if I comment out the keyboard.close method, I once again have a resource leak. Now, as I said, a resource leak does not cause a compile time error. The code will still compile and run. The danger is that if I continue to accrue resource leaks, I'm eating up memory. And over time, in a long-running program, it is possible that I will run out of memory and the system will crash. Okay, here's the complete code for Program 7. The results from my test run are in the green rectangle. If you had any problems, make the corrections. Run your code, make sure it's correct. Now, let's try another problem. I'm going to call this one Problem 7a. The only way to acquire competence in any programming language is to write code in that language. If you skip these programs, you're wasting your time even playing these lectures. And the first step in coding is actually understanding the problem domain. So let's work on that first. The graphic shown is a right triangle, which means that this angle is exactly 90 degrees. And if that's true, then the Pythagorean theorem will define the relationship between the sides and the hypotenuse, the side opposite the right angle, the one which is the longest side of any right triangle, the one highlighted in red. The relationship between the hypotenuse and the 2 legs is that the hypotenuse is equal to the sum of the squares, the square root of the sum of the squares of the 2 legs. So, suppose leg A is 4 units in length and leg B is 6 units in length. Then we can find the length of the hypotenuse by setting c squared equal to 6 squared plus 4 squared, or 36 plus 16, which sums to 52. And taking the square root of both sides of the equation, we get the hypotenuse c equal to the square root of 52, or about 7.2. Of course, the obvious question is, how do I get the square root of a number? Well, to solve any mathematical programming problem, we can get substantial help from the Java math class, and that help is documented in the online Oracle site. And this is what we've been using so far. But Eclipse also provides on-screen contextual help. So put your cursor right here, just to the right of the decimal point between math and PI. Then hit the control key and the space bar simultaneously, and you should get two screens just like this. They won't have the green and red borders. I added those to the slides to make it easy for me to tell you which box I'm talking about. But the content should be identical. The green box lists all the methods and constants that are available to any object of the math class. The top two are the constants E and PI. Right now, E is shaded, so the red box gives a brief description of E as a close approximation of the value of the base of natural logarithms. The one below is PI. If I move my cursor down to that line and left click, then PI will be the active constant, and the red box will show a definition of the constant PI. Both of these are constants, but the remainder of the listings are methods available to any math class object, and they cover an enormous range of mathematical functionality. Put your cursor right here, and now left click on the slider button in the green box and drag it down about this far. Then slide the cursor over and click on POW, short for power. The description of this method is in the red box. Method POW, power, takes two parameters. The first parameter is the number you're trying to raise to some power. The second parameter is the power you want to raise that number to. So this line of code will raise 5 to the third power, 5 cubed, and assign the result, 125, to x. Now, there are a couple things you need to be aware of, particularly when you're dealing with methods of the math class. First, note that both parameters of the POW method, the power method, are doubles. But I'm using it, I'm passing literal integer parameters. So, should I be getting a compile time error? Think it over for a minute. Don't waffle. Pause the recording. Make your call. Simple Boolean. Yes or no. Should I get a compile time error? Well, it's no. Remember this slide from Lecture 3. Lecture 3, slide 93. For numeric primitives, the value of any variable whose data type is a lower rank can be assigned to a variable whose data type ranks above it. All of the numerics, byte through float, have storage sizes less than or equal to the storage size for a double. So this works fine. A is a byte, B is a short, and I can use those as parameters. However, the return type from method POW is a double. So in this line of code, X has to be declared as a double. Note that even though long and double have the same size, both take up 8 bytes of storage, it is a compile time error to attempt to assign the output of the POW method to a variable of data type long. And of course, float won't work because it only has 4 bytes of storage. Now, slide your cursor down to method squirt, SQRT. It's an abbreviation for square root. And left click and note that the red box now contains a description of the square root method. I can use it as shown here. And the data type discussion we just had with respect to the return for method POW also applies to method SQRT, square root. Y must be a double. So, in Eclipse, in the project folder for week 7, create a new class, Program 7A. And here's the assignment for Program 7A. Code the solution and test for the required output. I used 4 and 6 here, but you might also try 3 and 4, which would output 5. Okay, this is what we just covered in Lecture 7. And here's where we're going in Lecture 8.